In this section, we're going to talk about vector-valued functions. Let's begin with the definition. A function of the form R of t. Notice the notation. We're calling it the way we would normally call a function, f of x, f of t, g of h, or whatever you might have. But note that the name of the function has this arrow over it. The same way we would normally write the symbol over a vector. Here, r of t is equal to f of t, I, plus g of t, j, plus h of t, k. This is in space. Or r of t equals f of t I plus g of t j, this one being on the plane, these are referred to as vector-valued functions. Where the component functions f and g, or in this case f, g, and h, are regular functions of a parameter t. Note that f and g, or in this case f, g, and h, are just regular functions, the way we're used to them. They accept a real value and they output a real value. I, j, and k are the unit vectors in the direction of x, y, and z respectively. So you'll notice that given a parameter t, the input to your vector-valued function, each of these, what are called component functions, will return a value. That value will be a component of a vector. Or in other words, a vector-valued function is a function that accepts a number and returns a vector. For example, we're going to sketch the function and evaluate the domain. Let's start off with a vector-valued function in the plane. R of t is given by 5 minus t I plus the square root of t j. Okay. All right, so first of all, let's talk about the domain of this function. In order for this function to be defined, each of its components must be defined. I can't very well say, oh, this vector function is defined only for some of its components. No, either the entire vector is defined or it's not. So here the domain will be the overlap. It'll be the intersection of the domains of each of the component functions. So the domain of f of t equals 5 minus t. Notice that's a linear function, and linear functions have a domain that's all real numbers. On the other hand, the domain of g of t, square root of t, that's only numbers that are greater than or equal to 0. Because again, these are real valued functions. No fair accepting any non-real arguments or returning any non-real values. So yes, we know how to take the square root of a negative number, but that would require us to use non-real numbers. We end up with complex or imaginary numbers. So here, this domain is from 0 to infinity. And really it should be 0 like this to infinity, because it does include 0. All right, so then the domain of the vector valued function is the intersection of these two, the overlap. So the domain of r of t, well, that's all real numbers, and this is not all real numbers, so the overlap will be this one right here. The domain is everything from 0 to infinity, including 0 up to infinity, like that. Okay. So now to sketch this thing, note that this has been parameterized, and this parameterized curve gives me an x value of 5 minus t and a y value of the square root of t. All right, so let's write that. X is equal to 5 minus t, and y is equal to the square root of t. Okay, here I could solve for t. That would give me t is equal to 5 minus x, and by substituting that in here, that's going to give us y equals the square root of 5 minus x. Okay. So this will give us the path along where this travels. Okay, so that's simple enough. That's a radical. It's facing to the left. It's a minus x, and it's shifted over 5 units. So here, this would look something like this, where this is 5. This up here would be the square root of 5. After all, when x is equal to 0, y would equal to the square root of 5 minus 0, or in other words, the square root of 5. And it is going back in this direction. Note that this does have orientation, meaning as your x value progresses, you start from here and go on in that direction. Now, this illustration might be slightly misleading. Let me graph this again by a slightly different method. Here I eliminated my parameter and said, okay, there's my curve. While this is true, there's nothing wrong with this. It is a little misleading. Let me do this a different way. Let me plug in some values of t and see what vectors we get. All right, so t is equal to something, and r of t would equal to, well, let's find out. Let's plug in 0 here. Okay, if we plug in 0, note here we did say that this goes from 0 to infinity, so 0 is the smallest number we could plug in. That's going to be 5 minus 0. Okay, so that's 5i. And then plus the square root of 0. Okay, well, that's 0j. Okay. Let me plug in the number 1. If t is equal to 1, well, that's going to be 5 minus 1. That'll be 4i. Plus, and then that's going to be the square root of 1, which is just 1j. Okay. Let me plug in the number 4. And let's say, well, why'd you jump that quickly? I don't want to have to take square roots of 2 or 3. I could. I just don't want to. Trying to illustrate a point here. 5 minus 4 would give me 1i. And here, the square root of 4 would give me 2j. And again, I could plug in 5, 6, 7. But here, I just want a few points. Then I don't want to spend too much time. So I'm picking things that are easy to come by. Notice that these are vectors. what is the vector 5i plus 0j? Well, that would be the vector that would go 5 units to the right, starting from the origin, from here to here. And it wouldn't go on forever. It would actually stop at that point. For 1, well, 4i plus 1j, that's the vector that would go 4 units to the right and up a unit. So there's a vector there. Oh, and it stops at that point right there. Okay, so sure, the vectors do seem to be stopping at the points along this path, just like I had a moment ago. I graphed that. 1, 2, I'll go 1 to the right and up by 2, something like that. Notice what the vector valued function is, though. It's not so much that, oh, here, I've gotten this curved vector, because that's kind of what it looked like at the beginning. It looked like, oh, I have this curved vector. But that doesn't make any sense. How do you have a curved vector? What you have is, you have a bunch of vectors, and they all end at a point on this curve. The vector valued function is not one curved vector. That's not what it means at all. It means I have an entire collection of vectors, all starting from the origin and all ending on the points that make up this curve. Like that. So this is the these are the vectors, and this curve is simply these are all the points where the vectors end. Of course, we don't need to worry about where they start. As long as we're talking about things in standard position, they always start at the origin. So this is a way of thinking about a vector valued function. Let's take a look at an example of this in space. We're going to go ahead and sketch the function. Now, yes, these are all the vectors, but when we sketch the function, we don't generally sketch the vectors. We simply sketch the collection of endpoints of the vectors. So here, we wouldn't really draw these arrows unless we had some reason why we wanted to. This blue curve is what we're after. So here we're going to sketch the function and evaluate the domain. And here we're going to do this in space. We're going to have t squared I plus 2tj plus 3 halves tk. Incidentally, we can write this in the other version, the other notation used for vectors. Here, we could also have written this one as 5 minus t comma square root of t. As long as we have those angled brackets, we know that's a vector. That's the first component, that's the second component. Over here, if we wanted to, and I often do want to because, I don't know, this just seems like too much to write. I don't want to have to write these extra symbols if I don't have to. T squared, comma, 2t, comma, 3 halves t. You are welcome to write either notation you like. You will notice that I use this one more often than this one, but they're both perfectly fine and interchangeable. Right. So here we go. The domain of this one is, well, each of these components is a polynomial. And the domain of any polynomial is all real numbers. So the intersection of all real numbers, and all real numbers, oh, that's all real numbers, right? Over here we had a restriction on at least one of our components, which restricted our domain in total. Here, the domain of each of these is all real numbers. So if each one has a domain of all real numbers, then altogether, the domain of the domain of f of t, g of t, and h of t is all real numbers. So the domain of the function must also be the same. All right, so there's the domain. So now let's go ahead and sketch the function. All right, this can get a little tricky to say, okay, I'm going to sketch a curve in 3 space. Okay, that even if I'm a very good artist, might be a little difficult to actually pin down, or even if I'm not a great artist, right? Or if I really know what I'm doing, but I have a hard time drawing things, It's also somewhat difficult to work with. So let's see how we can make this a little easier on ourselves. What I'm going to do is I'm going to take two of these components. I'm going to use x and y because, well, frankly, I just like working with x and y. And I'm going to eliminate the parameter just between those two. Okay? So I'm going to go ahead and take x equals t squared. I'm going to take y equals to 2t. And I'm going to eliminate the parameter. Here, all it takes is I can divide this by 2. So here I get t is equal to y over 2. And now I can take this parameter and plug it in there. So this will give me x is equal to y over 2 quantity squared. Or, if I prefer, I can even write that as x equals y squared over 4. Okay. All right, so what? Note that this is a cylinder. If you have in space an equation that is missing one of the variables, then this equation in two variables defines a curve on just one of the planes, in this case the xy plane. This will be the generating curve for a cylinder. You say, so is that my graph? Or what about this one? Well, that's not the graph yet, but this is a good start. Let's see how we're going to use this to make our job a little easier. Actually, a lot easier. All right, let's begin by graphing this generating curve. Yes, I'm going to graph this in 3 space, but of course it does exist on the plane. Okay, so my generating curve is, well, that's a parabola. Notice here that's a parabola that's it's facing out toward the positive half of the x-axis, right? Here, 0, zeros, oh, I should label this, x, y, and z. Here, this one is facing out in the direction of the x-axis. All right, here, if you had x is equal to 0, y would equal to 0. Okay, so 0, 0. If you had y is equal to either 2 or negative 2, x would equal to 1. So if y is equal to 2 or negative 2, y would equal to 1. So something like that. So you'd have a parabola. All right, well now that parabola will generate a cylinder. Since z is the missing variable, that means that the rulings of this cylinder will be parallel to the z-axis. So in other words, we're going to have this kind of an object here. It's like a folded sheet of paper. If I took a little sheet of paper and folded it over, you got something like this. That's what I'm looking at. The generating curve is this parabola down here, and then it propagates upwards this way. So that's the object I'm looking at. So here that's something like this, right? Okay. All right, so now what? We know we're not looking for a surface, are we? I thought we were looking for a curve, something like this. Well, we haven't really considered our third component yet. All right, so why are we looking at just these two components? Without the third component, we don't know how far up or down our vectors are. What we do know is, with just these first two components, we know that every vector will end somewhere on this sheet, somewhere on this surface. What that means is I've now narrowed it down to, oh, my vectors can be literally anywhere, to, oh, they got to follow alongside along the outer edge of this sheet. Which means now I can go ahead and plug in a few points, connect my dots, and it'll be nice and easy to follow. Let's go ahead and do that. Just a few points here. Note I can plug in any number I like, so I'll just keep things simple. If t is equal to, let's say, 0 to start with, then I'm going to have t squared, 2t, and 3/2 t as my components. Okay, so that's going to be 0, and that would be 0, and that would be 0. So I know that my curve is going to exist at the origin, 0, 0, 0. Okay, well, that definitely is a point on that sheet. Let's go on. Let's go ahead and say the number 2. Why 2? Because I don't have to do with fractions. So here 2 squared would be 4. 2 times 2 would be 4. And 2 times 3/2 would be 3. Okay, well, that would be 4 units out along the x-axis. All right, because this is my x right here. X equals, y equals, z equals. So it would be 4 units along the x-axis, 4 units along the y-axis, and then 3 units along the z-axis, so up this way. So my curve would be right around there. Okay, let's do a few more. I'm going to say the number 4. Well, let's see, that would be 16. 2 times 4 would be 8. And then 3/2 times 4 would be 6. So that would be 16 out along the x-axis, 8 units along the y-axis, and then 6 units up. So that would end up here. This is a little bit hard to see going this way. Let me go back the other way. Let me use a few negative numbers. Let's try -2. All right, well, that's going to give me -2 squared, that's +4. -2 times 2, that's -4. And -2 times 3/2 is -3. So here this will extend on down, which is fine. Cylinders go in both directions. And so here, that would be what? 4 units along the x-axis, so this way. And then -3 steps along the y-axis, so back this way, negative. And then 3 steps down this way. So that would be my point. So now, as I connect my dots, just a few dots, if in space, I would have no idea what's going on. But since I know they exist on this sheet, oh, I think I know what's going on. From this point, and remember, there is an orientation. As the numbers are getting bigger, as t grows, you're going from here to here to here. So it looks like I'm following along the outer edge of this sheet of paper. I'm taking my sheet right here and folding it up like that. And I'm starting from this bottom corner, and I'm wrapping around the sheet and coming around and then coming back up this way. And there we go. There is some orientation, so it does seem to be going in this direction. What we have is, essentially, I've got a curve like this that's going along a surface. Oh, but that surface is bent. Okay, so what I do is I first find the bent surface, and then I worry about putting a few points and connecting the dots. Here, this is just sort of wrapping around the outside like that. I suggest you try one. Go ahead and sketch and evaluate the domain. This will be a vector valued function in space. R of t will equal to t, comma, 3 cosine of t, comma, 3 sine of t. I suggest you do the same thing that I did before, and that's eliminate one of the parameters so that you can draw a surface, and then you can plot points along the edge of that surface. Right? It doesn't really matter which variables you use to eliminate the parameter. Here I said x and y. I eliminated the parameter for those two and then made a surface that was a cylinder with a generating curve on the xy plane. I could have done that with x and z or y and z. It doesn't really matter. That being said, right here, it does seem pretty obvious that two of them kind of belong together. So here you might want to make something happen with these two. All right, so go ahead and give it a try. Go ahead and evaluate the domain. That one shouldn't be terribly difficult. Just look at the domains of each one. And then go ahead and sketch by first eliminating a parameter, giving yourself a cylinder, and then mapping a few points along the outer edge of that. Go ahead and pause the video, and once you have a result, go ahead and unpause and we can go through it together. All right, so the domain is straightforward enough. We know that the domains of, well, let's see, that's a polynomial. It's got an infinite domain. Sine and cosine both have infinite domains as well, right? There's no restriction. Cosine, you can take the cosine of anything. Take the sine of anything. Now, the sine of something and the cosine of something are between -1 and 1. Right? That's the output. That's the range. But the domain, I can plug in anything. So the domain of f, g, and h is -infinity to infinity. So that means that the domain of r of t would also be from -infinity to infinity. It's the overlap. But since all three of them are the same, well then the whole thing is their overlap. All right? So now let's go ahead and I'm going to consider these two, and I'm going to try to eliminate the parameter. 3 cosine of t, that's equal to x. And y is equal, oh, no it's not, that's equal to y. And z is equal to 3 sine of t. All right, so that's my y, and that's my z. I'm not considering x for a moment. Okay, well I can eliminate the parameter here. And I can do that just using the Pythagorean identities. Here, if I divide both sides by 3, this will give me cosine of t is equal to y over 3. This will give me sine of t is equal to z over 3. I could square each of those. Okay, so that will square each of those. Cosine squared equals y over 3 squared. Oh, but now if I add these together, that's a Pythagorean identity. Cosine squared of t plus sine squared of t is equal to 1. On this side, adding these would give me y squared over 9 plus z squared over 9. Or if I prefer, I can leave the 9 over here, and I can write that as 9 equals y squared plus z squared. Here this looks more like an ellipse, and you realize, oh, the major and minor axes are equal to each other, which means it's a circle. Or if you transfer the 9 over this way, well then that's a circle of radius 3, which either way you get the same graph. So here, the generating curve of some cylinder is going to be a circle. Oh, this is one of those. This is a traditional cylinder, the kind that you're used to from when you first learned geometry in grade school. All right. So on the x, y, z coordinate system, we're going to start off with a circle on the YZ plane. Okay, note that circle has a radius that's equal to the square root of 9. In other words, a radius of 3. So that'll be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so that'll be the generating curve of your cylinder. So now that generating curve will propagate in the direction of the x-axis, because notice, since we're missing the x variable here, then that means that the rulings must all be parallel to that missing x-axis. Okay, so that means we're going to propagate that out toward us and in toward the paper. All right, so that'll give us that'll give something that looks like this. It's a tube. Here it's open on either end, so here this is just going through. It's a tunnel. So that means that whatever curve we end up with, whatever curve our vector valued function gives us, it will exist on the surface of this cylinder. Okay. All right, so now we can simply plot a few points along the skin of this object, along the surface of this cylinder, and then connecting the dots will be a lot simpler than having to graph out dozens or even hundreds of points to see a pattern otherwise. All right, so here we go. Let's plot a few points here. T. Let's see, x is equal to t. Y is equal to 3 cosine of t. And z is equal to 3 times the sine of t. All right. Let me not use 1, 2, and 3, right? I want to have something that I can take the sine and cosine of. So here, let's start with 0. Okay, and remember, I am allowed to use all real numbers, so anything's fine. Positive, negative, it's okay. In fact, let me start with a negative number. I'll put my 0 down here. So if t is equal to 0, well, then x is also equal to 0, because x and t are interchangeable. Here, y is equal to 3 times the cosine of 0. 3 times 1 is 3. And then, if t is equal to 0, z is equal to 3 sine of 0, which is 0. Okay, so that would give me a point that's, well, I don't travel along the x-axis or the z-axis, but I do go toward the right 3 steps. So from here to the right. Okay, so I'm at that point on the outer edge of that cylinder. Okay, so now let me plug in a couple of positive points and a couple of negative points. Let's just keep things simple. I guess we'll go with pi over 2 and negative pi over 2. Let's try that. All right, so if I have negative pi over 2, well, the x is the same. The y would be 3 times the cosine of negative pi over 2. The cosine of negative pi over 2 is 0, so 3 times 0 would stay 0. And then z would equal to 3 times the sine of negative 3 pi over 2. Well, negative pi over 2. The sine of negative pi over 2, that's negative 1, times 3, that would be negative 3. Okay, so then that would have, I would have to go, my x value would be negative. So I would go back away from us, away from the origin, not toward us in this direction, but away. Okay, I'd go away from us. Here you wouldn't go left or right at all. Y is equal to 0. And then you go 3 steps down. So from here you go back and down to about over here. Okay. Let's try positive pi over 2. Well, that's going to be very, very similar. That would be positive pi over 2. Here, 3 times the cosine of positive pi over 2, that's also 0. And 3 times the sine of positive pi over 2, that would be positive 3. So that would come out toward us, and then it wouldn't go left or right, but it would go straight up 3 steps. So 1, 2, 3 to the upper edge of this. Okay. Here, you might still have a hard time seeing this one. I'm going to do just a little bit more. Let me go with negative pi. Oh, I'm not sure why I changed colors there. I'm going to go with negative pi and positive pi. Okay, so that would be negative pi. 3 times the cosine of negative pi, that would be negative 3. And 3 times the sine of negative pi, that would be 0. So I would still be going back twice as much as before, so further back this way. And then I would go 3 steps to the right. Oh, no, that's negative. So 3 steps to the left, back over here, but then don't go up or down at all. So I will still be on the xy plane, and I would be over here all the way to the left, on the leftmost edge of this circle of radius 3. Okay. And if I plug in a positive pi, well, that'll give me pi. Here, 3 cosine of pi. That will give me positive 3. And 3 sine of pi, well, that would give me 0. So here I would come all the way out here. I would come out twice as far as this one did. And then I would have 3 steps to the right, but then I would not go up or down at all. So from here, come out, go right, and be sort of here on this outer edge of the cylinder. Right. Okay, so now let's connect our dots. We know we're starting from back here. The negative numbers gave us the ones way back here, and the positive numbers gave us the ones coming further out toward us here. Okay, so it looks like we have from here, we kind of come around to the underside of this circle, and then we come back over here to the right side. Then we're up at the top side. Then we come back down. Oh, that's spiraling, isn't it? So it kind of does something like this. Oh, let's see here. That's a little hard to draw. It's, but this is starting from on the left side. Then it's coming to, this is down underneath, so this is like at the bottom of this. And then it's kind of swooping back up, and that's on the right side. And then it goes up to the top, and then it loops back around so that you're back on the back side here. So you have an orientation where this is sort of spiraling, it's spinning. This is sometimes called a helix. Basically, you're taking something and you're just wrapping it around this cylinder. Note that I stop here, but that's only because that's the last point that I did, and I don't want to keep doing more of those. But this does keep on going. This would continue to spiral in both directions, because after all, the domain is infinite, so this would continue on that way and out this way as well. So it is important that you note orientation. In later sections, when we start using vector valued functions for calculus, meaning taking derivatives, taking line integrals and such, orientation will make a difference. It does matter which direction you're traveling in. Okay, so what about going back the other way? Here we see how we take a vector valued function. We can eliminate the parameters a little to end up with a surface, and then mapping points on that surface gives us our curve. In this case, it was a helix from the left to the bottom, wrapping back up to the right, then to the top, and then back down this way. So what about going the other way? How can I create a vector value function that represents some particular curve? All right, so let's take a look. Let's represent by a vector valued function the curve y equals 4 minus x squared. Okay? Don't make it any more difficult than it has to be. Here, we're simply looking for a way to parameterize both variables. We're trying to parameterize x and try to parameterize y. Okay, well, here y is already a function of x. You're trying to turn it into a function of t. So why don't you just replace x with t? Here, we can set x equal to t. That means y is equal to 4 minus t squared. That x gets replaced by that t. Oh, so then that means that our vector valued function, r of t, is simply, hey, that's my first component, and that's my second component. Are there other ways to parameterize this curve? Yeah, probably, but this one works just as well as in the other, so why not use this one? Now, this is really straightforward and nice to use, which of course means that we're not going to have too many of those, right? Let's take a look at something that's a little more realistic. Oftentimes, these vector valued functions are going to be used to describe some curve, not because we decided, oh, that's a nice pretty curve, but because it's the result of two or more surfaces intersecting. Just like in Cal 1, you have to find, oh, here's a curve, here's another curve, and we want to integrate. We want to find the area between here and here. Oh, well, we need our boundaries. We need to figure out where these two curves meet. Well, now we're going to have surfaces instead of curves. And those surfaces will intersect. But since they're in 3 dimensions, their intersection may not be individual points, but entire curves. So let's go and talk about how to do something like that. We're going to go and sketch and represent by a vector valued function the intersection between the surfaces that are given by 4x squared plus 4y squared plus z squared equals 16 and x equals z squared. Okay. All right. Here we're going to sketch what we're talking about. First of all, this, if you take the level curves, oh, that's a circle. Oh, that's an ellipse. It's almost a circle except the constants are different. Oh, and that's an ellipse. Oh, it's almost a circle except the constants are different. Okay. Well, in that case, that means that it's elliptoid. So that can be graphed. Looking at the traces, if I set z equal to 0, that'll give me so the xy trace, that'll give me 4x squared plus 4y squared equals 16. Okay, let me divide everything by 4 since it's a common factor anyway, and I'll get x squared plus y squared equals to 4. Okay. At the yz trace, at the xy trace, z is equal to 0. And here, dividing everything by 4 gives me that. Oh, that's a circle of radius 2. So on the xy plane, my trace is a circle of radius 2. Okay. Let me check my xz trace. That's where y is equal to 0. Okay, so that'll give me 4x squared plus z squared equals 16. That's an ellipse. It's almost a circle, except the constants are different here. Okay, well, with an ellipse, it's easier if I make the constant equal to 1. So here I can divide everything by 16. This will give me x squared over 4 plus z squared over 16 equals to 1. Okay, so now when z is equal to 0, x is either equal to positive 2 or negative 2. When z is equal to 0, x is equal to positive 2 or negative 2. When x is equal to 0, well then z must either equal to positive 4 or negative 4. Positive 4 squared over 16 or negative 4 squared over 16. Both of those are equal to 1. So here I would go up 4 units and down 4 units, plus and minus 4. Okay, so there's my ellipse. It's taller in the x direction. It's taller in the z direction than it is in the x direction. So I'm getting this sort of egg shape going. And the yz trace, well, it's exactly the same. Except instead of having an x here, that'll be a y. That'll be y squared over 4 plus z squared over 16 equals to 1. For the exact same reason, if I cover this one, or if I cover this one, it looks exactly the same, but one has an x and one has a y. So there we go. And for the exact same rationale, it'll be taller in the z direction than it will be in the y direction. So there we go. There is our surface. It's an egg. Something like that. Okay. Now what's our other surface? Oh, this one's much simpler. This one, it's missing y. Oh, that's going to be a cylinder. Whenever you're missing one variable, it's got to be a cylinder. Here, the generating curve, x equals z squared, that's a parabola. And, in fact, that's a parabola opening in the direction of the x-axis, right? It's on the xz plane, so it's on this plane. And since you have positive z squared equals to x, that means that you're opening up, that you're opening out toward the x-axis. So something like this. All right. Since y is missing, I know my rulings have to be parallel to the y-axis. So I'll have something like this. It's a little sheet of paper that's been folded over on the top and on the bottom. So a little sheet of paper folded over on the top and on the bottom. All right. Okay, so those are my two surfaces, and clearly they're going to cross in there. It's a little hard to see the actual intersection line, but it's going to be where this bends around and curves around the outside of this egg shape. One day in the not too distant future, we'll have extremely amazing technology where I'll say, computer, give us a 3D rendering of this, and out of the screen, a holographic projector will pop up and give us a perfect render, a 3D rendering of this floating right in the middle of everyone's eyes. And then I'll say, computer, intersect it with this, and it'll intersect that, and it'll clearly show the boundary in every tiny detail that you can imagine. And I will be very, very jealous of that future us, because right now that's the best we got, right? And that's not quite true, but well, no matter what we have, everything's two dimensions. So you get computer graphics to do it for you, it's still flat, right? So until the day we get very accurate three-dimensional things that we can manipulate and handle, everything's going to be a representation of on two dimensions. So we do the best we can with what we have. So anyway, that is our intersection. It's going to be where this slices through that egg, like that. And on the other side, this side actually looks pretty good. At least I can see that the shape of that curve. On the back side, it's symmetric, although it's really hard to draw that on the other side at a perspective. But in any event, that's the first part. We've sketched our object, and we sketched the line where they intersect. So now the question is, how do we represent that thing? Okay. Well, just like in the previous problem, we took one of our variables and just said, okay, that's t. And then we defined the other one in terms of that. I'm going to go ahead and do that here. I'm going to go ahead and call z. I'm going to call that one t. Why? Well, one thing is it does exist for both. I do have z is equal to, I do have z in both equations. I wouldn't want to pick y, which doesn't exist in this one over here. I can either pick x or z. And here, if I say x is equal to t, then z would have to be the square root of that. And well, I think I want to avoid the square root if I can. So I think I'd rather let z equal to t. And that way x can equal to t squared. All right. So in fact, I've kind of given that away, right? That's what's going to happen. Here, I'm going to take z, and I'm just going to call it t. Again, I wouldn't want to use y because it doesn't exist here. And I want something that's related to all three, both of my equations, because that's where the intersection is. It relates to both of them. And if I let x equal to t, well, then z would involve a square root. That's how I isolate z. Oh yeah, let me not involve square roots if I don't have to. Now, I have other squares, so I probably will need a square root eventually, but at least let me not start that way. So here, z is equal to t. Okay, well, over here, I have a very complicated equation of both x and y and z. But here, this one's simple. So let me start with simple. That's generally the rule. If you have something simple and something complicated, start with simple to try to isolate some variables, to try to make some substitutions, and then move on to the harder ones. So here, if x is equal to z squared, well, then that means x is equal to t squared, because we've just replaced z with t. So now in this equation, I can isolate my remaining y, and it looks like x and z are already in terms of t. So let's go ahead and do that. Here, I can take 4, instead of saying x squared, I can say t squared squared, plus 4y squared, and the y is what I'm going to try to isolate here so I can figure out its parameter, its parameterization, and then plus z squared. Well, we know z is equal to t squared, like that. Here, let me go ahead and take this stuff and subtract it over. So that'll give me 4y squared equals 16 minus t squared minus 4t to the fourth. We divide everything by 4. It can be y squared equals to 4 minus 1/4 t squared minus t to the fourth. And finally, let me take the square root here. So it looks like I have y equals. Now, this seems a little strange. Plus or minus, right? When you take a square root, aren't you supposed to have 2 of those? So how do I know which one? Well, let's see. Well, if I have y's positive square root, well, then that's going to be this part up here. Oh, yeah, but don't I want the whole thing? Oh. So it's not like I'm choosing one. I actually need them both. By having y be potentially positive or negative, it allows me to track not just these, but also these down here. So here we get y is equal to plus or minus the square root of 4 minus 1/4 t squared minus t to the fourth, which now suggests that our vector valued function should actually be given in 2 parts, one for the upper and one for the lower. So here I'm going to define this using 2 vector valued functions. I'll call one of them R1, and I'll call the other one R2. Here, x is equal to t squared. I'm going to call R1 the upper half of this, so I'll use the positive square root. That would be 4 minus 1/4 t squared minus t to the fourth, comma, and then z is equal to t. And then the other one is exactly the same, except I'll use the negative root to represent the bottom half. And these are our results. It turns out we need 2 vector valued functions to fully represent that curve. And that makes us happy. Okay. You may wish to give this a try. Or not. Go ahead and sketch. This one's simpler, I promise. The sketch anyway. Sketch and represent by a vector valued function the intersection between the two surfaces z is equal to x squared plus y squared, and this is not a mistake, it is a constant. Z is equal to 4. Here, I'm going to make a suggestion for a parameter for you to use. Here, you could just as easily say, oh, let x equal to t, or y equal to t, or z equal to t. However, whenever you have the sums of squares, trigonometry often comes into play. So here I'm going to make a very strong suggestion. I suggest you use the parameter x is equal to 2 cosine of t. Okay. Generally, whenever you have something like x squared plus y squared, you're going to see x equals some multiple of cosine of your parameter, and y will be some multiple of the sine of your parameter, just like in trigonometry. So go ahead and give this a try. Go ahead and pause the video, give yourself the time you need, and then once you're ready, go ahead and unpause, and we'll go through it together. All right, so we're going to sketch this. This is a paraboloid. That's a parabola. That's a parabola. That's a circle. X squared plus y squared equals to some constant. Okay, so then that's a parabola in every direction except for the xy plane. My x, y, and z coordinate axis. If I'm looking at the yz trace, well then x is equal to 0, and that's a parabola facing up toward z. Okay. If I look at my xz trace, then y is equal to 0. Oh, but again, that's a parabola facing up toward z. And then here, if z is equal to 0, my xy trace, that's a point. That's the origin. Technically, it's the circle of radius 0, which is just a point. But if you took any other value, you could say, for example, z is equal to 1. Then you have x squared plus y squared equals 1, which that means that if you're one step above the origin, you have a circle of radius 1 tying this together. And higher up, you'd have other circles of other radii tying this together. So this is going to be a paraboloid. One of my favorites because it's one of the few that I can actually draw out well enough. Here, this one is, it's a plane. Z equals to 4. That means you don't care what x or y are. You can have x or y in any direction, as long as z is equal to 4. So that's just like on the xy plane when you have something like x equals to 4, that would just be a vertical line. You don't care what y is. Or if you have something like y equals to 4, that would just be a horizontal line. Again, you don't care what x is. Well, here, z is equal to 4. That means you want the height to be 4. And you don't care what x or y are. So you end up with a plane that's 4 steps above the xy plane. Okay, so where does this paraboloid cross that plane? Right there. It's a circle. In fact, not only is it a circle, it's a circle of radius 2. All right, because after all, if z is equal to 4, 4 is equal to x squared plus y squared. Oh, that's a circle of radius 2. All right, so we've gone ahead and sketched it. So let's go ahead and represent it using a vector-valued function. I've kind of given it away. Here, z is equal to x squared plus y squared. Here, z is equal to 4. Okay, so replace your z with 4. It's going to be 4 equals x squared plus y squared. Oh, but we're saying we want x to be 2 cosine of t. Okay, so 4 equals 2 cosine of t squared plus y squared. Okay. All right, so then we can go ahead and subtract this over this way. So that'll give us y squared equals 4 minus, if I square this out, that's 4 cosine squared of t. And that's a Pythagorean identity. 1 minus cosine squared of t, that's sine squared of t. Oh, but everything's multiplied by 4. Okay, then that's 4 sine of squared of t. That's just a Pythagorean identity. So now if we want to isolate y, we can take the square root of both sides. And this will give us plus or minus the square root of 4 sine squared of t. Which incidentally, we can take the square root of that. That would give us y is equal to plus or minus 2 times the sine of t. One thing to note is that unlike the previous problem, that plus or minus is redundant here. The reason it makes a difference over here is because if you take this expression, take the square root, it's going to be positive. You can't get the negative out of a square root. If this was negative, if this is positive inside, the square root is positive. If it's negative inside, you don't get a square root. It's an imaginary number. So this will always be positive. So the plus and minus is the only thing that allows you to have the upper and the lower half. Here, sine of t can be positive or negative. It bounces back and forth between 1 and minus 1. So having the positive 2 sine of t, that'll get you your full range from minus 1 to 1, or actually from minus 2 to 2. And having negative 2 sine of t will also get you the full range from minus 2 to 2. So here you have a redundancy built in. You only need the positive. Or if you want to, you could say I only need the negative. Here I'll say I only need 1. The positive or the negative. So I'll go ahead and keep the positive just because I'd rather not keep a negative if I don't have to. So in that case, this gives us our parameterization. We have that, well, we already, my hint was x is equal to 2 cosine of t. And anytime you have the sum of squares equals to something, you should keep that in mind, that a Pythagorean identity is probably the correct way to go. We now find that y is equal to 2 sine of t. And here, we don't need a variable to parameterize z. Z seems to be a constant here. Remember, we're not looking at every value of Z on the paraboloid. We're simply looking at the intersection between the paraboloid and the plane. And on this circle, Z is always 4. So your parameterization and your vector value function therefore looks like this. R of t is equal to, my x is 2 cosine of t. My y is, I'm going to keep the positive one, although either one would work, 2 times the sine of t, comma, and that's going to be 4. Okay, just like any function that we have of a single value, like f of x, the traditional function that we're used to, we can perform operations on these functions. Just like you can take an f of x and a g of x and add them together, we can do the same thing with a vector valued function. Here, thankfully, it's done component-wise. Definition? Let's begin with a vector valued function. Let r of t equal to f of t, comma, g of t. Then the limit as t approaches some constant, we'll call it a. The limit as t approaches some constant a of r of t is simply the component-wise limit. The limit as t approaches a of f of t, comma, the limit as t approaches a of g of t. And this is still a vector. Now, of course, this does assume that both of these limits exist. Assuming the limits of the components exist. Likewise, this is true for a vector valued function in the plane. It is also true in space. So let r of t be given by f of t, comma, g of t, comma, h of t. Then the limit as t approaches a of r of t is equal to the limit of the components. But notice that the components are just regular real valued functions, which means that they are the same limits that we see in Cal 1, which is great, because if you remember, the limits in Cal 1 are what allow us to then define the derivatives and the integrals, which means that if the limits are done component-wise, that gives us great hope that derivatives and integrals will also be component-wise. Things will be nice and simple because each component can be handled on its own. And since each component is a regular real valued function, a lot of what we learned in Cal 1 and Cal 2 still applies. Now, we can't assume that just yet, but that is hinted at here. Here, again, provided that all limits exist. One thing to note, so that's the end of our definition. One thing to note, the limit of the vector valued function is a vector. Okay? So when you say this limit as t approaches a of r is equal to some limit L, remember L is going to be some vector. What's more is that it does, because this is the limit in the traditional sense of a real valued function, the limit of the vector valued function will share the same epsilon delta definition of the limit of the components. Namely, if you have the limit as t approaches a of r of t. First of all, that limit will be a vector. So here, don't say L as if it were a number. It's going to be a vector L. That's equal to L if and only if, and then we have the familiar statement. For all epsilon greater than 0, there exists a delta greater than 0 such that the distance between t and a being smaller than delta, the difference between the absolute value of the difference between t and a, if that's small enough, that implies that the magnitude, normally we would say absolute value, but since these are vectors, the absolute value doesn't mean anything, but the analogous operation would be the magnitude. The magnitude of the differences between r of t and L is less than epsilon. This is the exact same statement of the epsilon delta definition of a limit that you see in Cal 1, except here, instead of having the difference between f and L as two numbers, here we would have the difference of r and L as two vectors. And to take the absolute value of vectors, that doesn't make any sense. Oh, but the analogous statement would be we're going to take the magnitude of the difference of the vectors, and that's going to be very small. In the next sections, we'll see that this actually leads to some very simple definitions for the derivative and the antiderivative of these kinds of functions, these vector-valued functions. But for now, we're going to start off with one very nice property, and that's the extension of continuity. So this is a definition, and this nicety, the fact that you can take limits of vector-valued functions component-wise, will lead to a lot of other niceties. Right? Since the limit is used to define other concepts, then this component-wise property will be inherited by those other concepts. And here we simply see the first iteration of that. We're going to begin with a vector-valued function. And we'll use the same symbol we've been using, r of t. Let's let that be a vector-valued function. And let t equal a be a point on the vector-valued function r of t. If the limit as t approaches a of r of t, assuming this limit exists, and the limit as t approaches a of r of t equals r of a, then r of t is said to be continuous at t. Oh, not at t, at a. It's said to be continuous at a. If you have continuity for every point on an interval, if r of t is continuous, on all points in an interval I, then we say r of t is continuous on I. One thing to note about this definition is that it does conform with the epsilon delta definition for continuity that you see of regular valued functions. And of course it should. After all, these vector valued functions are simply the amalgamation of regular valued functions. So whatever regular valued functions can do, it stands to reason that they generalize to these vector valued functions. So here, a note, as I just said, if you take your vector valued function, r of t, it is continuous at t equal to a if and only if for all epsilon greater than 0, there exists a delta greater than 0, such that the distance between a and some nearby value c, if that's less than delta, then that implies that normally we would say absolute value, but since these are vectors, we say the magnitude of r of a minus r of c should be less than epsilon. So this is the analog to the epsilon delta definition of continuity that you see in Cal 1. The only difference here is instead of f of x and f of I believe we use c there as well. F of x minus f of c. Here you have vector valued functions rather than typical functions, and here we have magnitudes, which is the analog for the absolute value. So no major change between what we mean by continuity and really not much in the way of how we think about continuity. Rather just for separate components rather than just one. So for example, let's start off with an example of a limit. If you want to take the limit as t approaches, let's say 0, let's say of e to the t, comma, sine of t over t, comma, e to the minus t. Here, that's nothing more than the limit as t approaches 0 of each component. So here you could think of this as just limit as t approaches 0 of e to the t, comma, the limit as t approaches 0 of sine of t over t, comma, the limit as t approaches 0 of e to the minus t. Here, this, you just substitute. All right? If t approaches 0, e to the 0 would be 1. Here you cannot substitute, because if you try to substitute, you get the indeterminate form of 0 over 0. Right? Oh, but if I can't substitute because it's of an indeterminate form, I can use L'Hopital's rule. Oh, the derivative of the sine of t is the cosine of t. The derivative of t with respect to t is 1. Okay, so cosine of t over 1, that's just cosine of t. Okay, can I plug in 0 now? Yeah, now I can, because cosine of 0 is just 1. Here, as t approaches 0, e to the minus t is e to the minus 0, or in other words, e to the 0, which is 1 again. And there we go. The limit as t approaches 0 of this vector valued function is this vector. And speaking of continuity, let's how did I misspell that twice? There we go. Let's discuss the continuity of the vector valued function r of t equals to the square root of t, comma, the arcsine of t, comma, t, like this. Really, we want to just discuss the continuity of each individual one and then see where they overlap. So we want the overlap of the intervals over which the components are continuous. All right, so as we see here, we need the limit to exist, and we need it to be what you get when you just plug in the number. All right, so let's see what we get here. Here, this is not defined so long as t is less than 0. Okay, so the square root of t is not defined when t is less than 0. Okay, what about the arcsine of t? Well, that's only defined between -1 and 1, isn't it? The arcsine of t is only defined on the interval from -1 to 1. It's continuous everywhere in there. It never has any jumps, skips, or breaks, but the domain is only from -1 to 1, including the 2 endpoints there. And then t, oh, well, that's defined and continuous for all real numbers. Now, for both of these, they are, wherever they are defined, they are continuous. Right? Think about the graph of the square root function, something like this. Wherever it does exist, it is continuous. Same thing for the graph, if you think of the graph of the arcsine function, something like this, where it's only defined between -1 and 1. But wherever it is defined, it is perfectly continuous, right? And here, of course, polynomials are continuous and defined for all real numbers. So here, where's the overlap? Okay, well, this is only defined for numbers greater than or equal to 0. Here, this is only between -1 and 1. And here, this doesn't give any further restrictions. Okay, so we simply want everything greater than or equal to 0, but still less than 1. Okay, so then that means that R of t is defined and continuous yeah. On the interval from 0 to 1. Right? Here, this is only defined for positive numbers. This is only defined from -1 to 1. So the overlap is the positive numbers that are less than 1, or less than or equal to 1. And there we go. Here, t doesn't contribute anything. It's defined for all real numbers. It doesn't give any other restrictions. So this would be the statement that we're looking for. And that brings us to the end of our section. If you have any questions, comments, problems, or concerns, please make a note of those, reach out, and I'll do my best to help you as soon as I can. I hope everyone has a nice day.